and record. Okay, so the working problems will be similar to what we'd see on Professor Ellis's exams. This is for the second exam. So let's get started. First, we're going to just look at an example of a partial fraction decomposition. We have negative 20x plus 56 over x minus 1, x plus 5, and x squared plus 1. Okay, so the first thing we do in any partial fraction decomp is look to make sure that the numerator is of the lesser power than the denominator, because otherwise we have to perform the long division. But as we can see here, we've got at most x to the fourth in the denominator and at most x in the numerator. So we can just go right into the decomp. We're going to have negative 20x plus 56 over just substitute that as b. I'm going to set that equal to a. Here, so A over x minus 1 plus b over x plus 5 plus, and this is important, cx plus b over x squared plus 1. And we need to use cx plus d because x squared plus 1 is not going to factor. There's nothing we can do with that, and so we need to account for the x. Solve problems like this. Obviously, we're going to multiply through to get our common denominator. So negative 20x plus 5 is equal to x plus
56.
What's that?
56.
Oh, my bad. Thank you. All right. A times x plus 1 plus b times x minus 1 x squared plus 1 plus cx plus d all times x minus 1 x plus 5. It's a little messy, but I'm less space than usual here. Now what we're going to do is we're going to set x equal to different things so that our factors cancel, and we'll have an easier time solving these.
I have a question real quick.
Ask away.
After what is that?
This here?
Yeah.
This is an A. Sorry.
Thank you.
I apologize. My handwriting's a little weird on this thing. Just calibrate it.
Is then a C, that is a plus C, and then
Right, this is just a parenthesis here. And then the plus C, x plus d. Okay, so for starters, we can see that if we let x equal to 1, this portion and this portion will both cancel out, which will let us solve for a very easily. So for x is equal to 1, we have negative 20 times 1 plus 56, which is just going to come up to 36, is going to be equal to a times 6 times 2 plus b times 0 plus cx plus d times 0. So those cancel. We're left with 36 is equal to 12a. A is equal to 3. So we'll store that up here for now. I'm going to need more room. So a is equal to 3. All right, so we'll just get this from here.
It's an expo markers on this.
Yeah, it's a lot easier.
There's two to the left of you.
Yeah. But we need to record this so that people can see it is the problem. There's no cameras in here, so we have to share the application.
Okay.
So next we're going to solve for b by saying x equal to minus 5. So when this happens, we have negative 20 times minus 5 plus 56. Set that equal to a times 0 plus b times, we have negative 6 times 5 squared, 25, 26 plus cx plus d times 0. Cancel, cancel. And we are left with the 156 is equal to 156 is equal to negative 156 times b. So our b is going to be equal to minus 1. All right, now when we solve for cx plus d, things get a little bit trickier, mainly because there's no real x that we can plug in to conveniently cancel that stuff out.
I hate this problem.
They're a bit lengthy. But one thing that we can do is set x equal to I. Now, I is, whether or not you've learned this yet, the irrational expression of the square root of minus 1. Technically, you can't take the square root of a negative, but this is how we accommodate for that. So if we set x equal to I, then we're going to plug into our initial equation. Negative 8 times I plus 56 is equal to, we have, let's see here, our a will be times 0, b will be times 0 because of the x squared plus 1. So x is equal to I squared is minus 1, minus 1 plus 1 is 0. So that takes care of our a and our b. And we're left with cx plus d times I minus 1 times I plus 5. All right, so leave this side alone. Negative 20i plus 56 is equal to cx plus d times, factor this through, and we'll have minus I, positive 5i, 4i, minus 5, minus 6. It should be yes, yeah, minus 6. Okay, so then we just factor the other side through. Negative 20i plus 56 is equal to, let's see here.
I squared equals negative 1, right?
Yes, which is why we can just combine our I squared factor with our negative 5. So this is going to be equal to negative 4c minus 6ci plus 4di minus 6d. Now, normally we'd be a little concerned that we still have i's left over, but if we look at this, this is just a simple system of equations that we've solved before. We take our factors of I and we set them equal to each other, and we take our factors of, say, I to the 0 in this case. So we'll have negative 20i is equal to negative 6ci minus plus 4di. So our i's will cancel. That's just an equation. And then 56 is equal to negative 4c minus 6d. So we have a simple system of equations that we've learned how to solve for before. This comes out to c is equal to minus 2 and d is equal to minus 8. And you can solve for that with substitution or elimination. It really doesn't matter. But the final partial fraction decomposition leaves us with 3 over x minus 1 minus 1 over x plus 5 plus negative 2x minus 8 over x squared plus 1. And that is our final partial fraction decomposition. So a little bit lengthy, but on an exam or quiz, that's pretty much far as you'll have to take something like this. We're to solve an integral in addition to all this algebra and systems of equations. If we're all set with that.
I have one little question.
Ask away.
How did you get C equals -2 and D is -8? You said you did what you said,
So you can use one of the methods for solving systems of equation. Let's say we take some room here.
Would it be solve like one of the equations for one of the variables, and then you plug that in the other one?
So like we'd set, say, 4C equal to -56 minus 6D. Divide that by 4, so we know what C is equal to 6D over 4.
It'd be 56. Be 54.
Right, sorry about that. Thank you. So take what C is equal to, plug it into your equation, solve for D, and then use your... Exactly. No problem. All right, so we're going to move on to, it's Riemann sums now. One thing you might see on the exam is actually to analyze the properties of Riemann sums. I don't know if you remember that table we worked on in class, but it's a good thing to have your formula memorized. We're actually not going to look at that. We're going to look at a given function. Let's say we don't know what this function is, but we know that for all intents and purposes, we're going to call it f of x, and it's greater than 0. We know that f prime of x is greater than 0. We know that f w of x is greater than 0. And we know that f triple prime of x is equal to 0. Now, why am I doing this? Well, what we want to know is what sort of approximations we're getting. So, multiple parts here from the left, right, trapezoid, midpoint, and Simpson's rule. We want to know what sort of approximation we're getting. Is it going to be greater than the integral? Is it going to be less than the integral? Is it going to be exactly what we're looking for? So the best way to figure out something like this is to get yourself a general picture of what your function is going to look like. So we'll put up our axes over here. X, Y, smart. Y. Okay, so we know that f of x is greater than 0. So this function is going to be somewhere above the x-axis. We know that f prime of x is going to be greater than 0. So we know that this function is increasing. We know that f double prime of x is greater than 0, which means we know it's concave up. Forms kind of a bowl shape. So at the end of the day, our function looks something like this. Now we can just take our different approximation methods and see exactly what we would get. Say we start at the left. Draw your awful.
Wait, how do we know it like that?
What's that?
How do we know that f is going to look like that?
F prime is increasing, and double prime is writing it down. F double prime is concave up, and then was F triple prime?
We haven't used it yet.
Okay, so those are the other two. So F prime is increasing.
So if f prime is greater than 0, it's going up, and so if it's less than 0, it'd be going down.
Right. So say our f prime was less than 0, then our function would look. It's still going to be concave up. So more like this.
Okay. If it was, but if f double prime was, it'd be concave down then. If it was less than 0, right?
We don't know what the function is, so there's no real way to tell. These are just our given parameters.
Okay.
But f prime and f double prime don't necessarily both need to be negative or positive. Example, we could have an increasing function that was also concave down like this. See, it's going up, but we've got concavity downwards. So there's really no direct relationship that we can solve for with those without any sort of function. This is just really to get us a picture of what we're looking at with the approximations. So, like we said before, this is a general picture of our function. It's not perfect, but we don't really know any way to make it perfect. So let's take a look at the left-hand approximation. Draw rectangles starting at the left points. So have something like this, something like this, this. As we can see, the tops of our rectangles are all very much below what our actual function is. So by that logic, we know that our left-hand rule approximation is going to be an underestimate. Now, in order to solve for the right hand, we do the same exact thing. Just get rid of these rectangles here. Fix our function up a little bit. How did this thing get so off? So if we start from the right-hand side, we have very obvious over. Tops of our rectangles, the areas of our rectangles are greater than that of the area under the curve. So the right-hand rule in the case of this function will be an overestimate. Right. Now, things get a little trickier with trapezoid and midpoint in terms of approximation, but remember how these particular lines work. They're actually pretty simple. So axis back here, get the function back here, and all right. So trapezoid rule. In trapezoid rule, we take 2 points here, here, draw the line. Here, here, draw the line. Wow. I am very sorry about this. Give me just a moment. At the start. Let's see if California thinks that I'm good. Much more. Okay, so we have our function. Now, when we take our trapezoid estimate, we basically take 2 points here, 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 draw the lines between them, sum of the bases times the height, etc., etc. Now, the important thing to remember is that these lines essentially represent secant lines. They touch our curve at 2 points and no more. Now, if we look at this, we can see I've exaggerated a little bit here for estimation's sake, but I'll make it more obvious here. So this is a secant line, which is what the tops of our trapezoids represent. And we can see that there's this little bit of overestimation caused by the trapezoid rule. So the trapezoid rule is an overestimate in the case of this function. Now, by the same logic, we can take a look at our midpoint rule and figure out what sort of approximation we're getting there. So the midpoint rule, we have our change in x, right? Delta x, and that's going to be the same space in between each one. In this case, we take the center point as our estimation. Now, it's very hard to see here, so I'm going to blow it up a little bit. But it's important to remember that our midpoint is essentially taking a secant line. So in the case of this concave function, we can see just a little bit of underestimation. So midpoint is going to be an underestimate by that logic. Simpson's rule, and this is where the f triple prime of x comes into play. So, given all these derivatives, now we don't know specifically what the function is, but since we're given that the third derivative of x is equal to 0, we know that at most our function is going to have some factor of x squared. That's as far as it can go, because first derivative then would be 2x, second derivative 2, third derivative 0. So we can see that that's the highest we can get, and we know that since Simpson's rule uses quadratic equations to approximate the curve, that this is actually an exact estimate for a given function. Okay, so that's a pretty straightforward approach there. Know your formulas for it. Don't forget about error bounds and things like that. They might show up. We're going to move on now to trig substitutions. Now, these are not particularly pleasant, but got it. So I'm going to have integral of root 5 to root 5 over 3 of t fifth over the square root of t squared plus 5 dt. Now, on a test or on this upcoming exam, what we'll probably have happen is we'll have to perform the substitution but not evaluate it. So we just want to convert this integral into something that we could evaluate using trigonometric substitutions. In this case, close. Yeah, I'll account for this 5 now here. But t is going to equal to the square root of 5 tangent theta. All right. So then our t squared is going to be equal to 5 tangent squared theta, which is also going to be equal to, by trigonometric identities, 5 secant squared of theta minus 5, which means t squared plus 5, what we have in the denominator, is just going to equal 5 secant squared theta. 5's cancel. And then we have to account for t, which is going to come out to the square root of 5 secant squared theta d theta. We have all our significant points. When we do convert this integral to something useful, we need to make sure that we convert our bounds of integration into terms of t as well. So we're going to have 5 is equal to 5 tangent theta. Tangent theta will be equal to 1, and theta to the tangent inverse of 1, which is pi over 4 by our sine cosine unit circle. So our bottom integral is going to be, the lower bound of integration is going to be pi over 4. Using the same method, subbing in for our t, we have the square root of 5 thirds is equal to root 5 tangent theta. Divide the root 5 over, and we get the square root of 1/3 is equal to tangent theta. Theta is going to be equal to the tangent inverse of root 1/3. And we know from our unit circle that's going to come out to pi over 6. Okay. So we have all our information. Now we just need to plug it all into the integral. So I'm just going to erase this and put our new answer up here. So come out as the integral from pi over 4 to pi over 6 of 25 root 5 tangent to the 5th theta, that's based on our t to the 5th, divided by the square root of 5 secant squared theta, which we know from this portion down here. And then we have to sub in our dt and our d theta for dt, so we multiply by root 5 secant squared theta d theta. And that will be our final answer.
Oh, we're not gonna like think so long.
We're not going to evaluate it. It's a time-consuming process, and in all likelihood, you won't be asked to do it on the exam.
Okay, can I ask where you got 25 from?
This 25 here?
Yeah.
All right, so our t is equal to root 5 tangent theta, right?
Yes.
Our initial,
T to the 5th.
right, t to the 5th. So just evaluate t to the 5th based on this. If you're looking to know where the 25 came from, we have root 5 times root 5 times root 5 times root 5 times root 5. Tangent to 5th theta. Root 5 is 5. Root 5 is 5. 25 root 5.
Oh, okay.
Tangent to the 5th theta.
Thank you.
No problem. Okay, so I believe I have got 2 more problems for you before I open the floor up for questions. I'll have different problems to show examples of tomorrow. Another good place to look for example problems is on Professor Alex's website. So now we're going to look at a bit of differential equations. We're going to solve an initial value problem, relatively straightforward one. X, y squared, y prime is equal to x plus 2. Now, at first glance, we're not really sure what to do with this, so let's start by isolating our y prime. Also important information, my apologies, our initial value y of e will be equal to 2. So let's start by isolating our y prime or our dy dx. That's going to be equal to x plus 2 over xy squared. We can separate this numerator into 1 over y squared plus 2 over xy squared. And then we have a factor of y here that we can move, so dy dx will be equal to 1 over y squared times 1 plus 2 over x. Cross multiply y squared y is equal to 1 plus 2x over x dx. So we can see it's just a simple separable differential equation. We can just integrate both sides. Y to the third over 3 is equal to x plus 2 ln absolute value of x plus constant. We're going to call it C1 because we're not quite yet. Multiply our 3 over and take the cube root of it to isolate y, and we get y is equal to the cube root of 3x plus 6 ln absolute value of x plus c. Now we have our initial condition, y of e is equal to 2, and solve for our c. So 2 will be equal to the cube root of 3e plus 6 ln absolute value of e plus c. make this easier to work with, we'll cube both sides to get rid of the cube root. 2 cubed is going to be equal to 8, and that's equal to 3e plus 6 ln of e is just 6 because the ln of e is 1 plus c. Subtract over the 6, subtract over the 3e. 2 minus 3e is equal to c. So the solution to this differential equation, given our initial condition, will be y is equal to the cube root 3x plus 6 ln of x plus 2 minus 3e.
Question real quick.
What?
When you have the ln underneath the square root, is that an n instead of brackets or supposed to be an n?
What, this right here?
Next one, left, middle. I think that looks like an n.
This, well, that's ln.
Oh, that's your version of ln. Oh, okay. Oh, I'm blind. Sorry. Okay. Sorry.
It's no problem. So, just a simple initial value problem, separable differential equations. You see something like this, try to isolate your x's and y's, see where you can.
Is that the answer?
Yeah, that's as far as you can take it. Okay, so I've got one more.
Oh, is the bottom the answer?
This is
Okay,
yeah, this is the answer right
Thank
here.
you.
Bottom right is the answer to this problem. This is our on the bottom left is our general solution to this particular differential equation. This is the particular solution with respect to this initial condition. Okay, so one last problem here. All right, so now we're going to use Euler's method. So we're given this function, differential equation, y prime is equal to 8 minus y. We're given that y of 0 is equal to 4. We're given that delta x is equal to 0.5. And we want to approximate y of 2. So this is relatively straightforward, just plug and chug, so to speak. We have 0 is equal to 0, y0 is equal to 4, and then we'll solve for all of our x's now just to make it easier. x1 is equal to 0 plus 0.5 is equal to 0.5, x2 is equal to 0.5 plus 0.5. 1, x3 is equal to 0.5 plus 1 is equal to 1.5. And our last x, x4, is equal to 0.5 plus 0.5, the 2 that we're looking for. So that's as far as we need to take it. Now we use our formula to solve for y1. Our y of n minus 1, in this case y0, is equal to 4 plus, and we have our delta x, 0.5, times the slope given by our equation here. So, let's see, 8 minus...
How do you get y to 1?
What's that?
How did you get
It's using this equation. So we say 0.5 times when you plug in f of our 0 and 4 into y1. So there's no x in our function up there, it's just y we're using?
Yeah, it's not a function, it's a differential equation. We're essentially solving an initial value problem, just by approximations. So solve for this 4 plus 1/2 times 4, that's equal to 6. value 6 plus 0.5 times, in this case it will be 6 minus 4. So that's 1/2 to, that's equal to 7. Y3 is equal to 7 plus delta x times our slope, which is going to be 8 minus 7, which is 7.5. And I realize I gave the wrong thing here. So that's going to be 0.5 times 6 minus 4. That's better. That's where we get our 1. Okay? And then our final value of y4 is equal to 7.5 plus 0.5 times 7.5.
Why is the last one 7?
8 minus. What's that?
Why does it go a minus 4, 6 minus 1, and 8 minus 7?
I'm sorry, this should say 8 minus 4.
Oh.
Okay.
Sorry about that. So this will be 0.5
Oh, it
times
continues as 8.
8 minus 7.5.
Wouldn't it be a minus 6 then for y2?
Hmm?
Would it be a minus 6?
Yeah.
Oops.
Oh, I am so sorry about that. Just get flustered up here. 8 minus 6. There we go. Okay. So now that we've corrected all the previous steps, we evaluate our last step here. 7.5 plus 0.5 times 8 minus 7.5 is 0.25. So that's going to be 7.75. So by Euler's method, y2 is approximately equal to 7.75. That would be our final answer. Okay, so that's all the example problems I have for you. Any general questions on anything you were wondering now? Hope to see some of you tomorrow. Have a great day.